Hi, it's Caitlin from the Ocean Tracking Network. In this course, Jonathan Pai, Director of Data Operations at OTN, will teach you how to make your data compatible with spatial mapping packages. You'll learn how to create summaries and plots of animal movement using Tidyverse, how to pull in a bathymetric map of the study region, plot stations onto the map, perform network analysis, and more. By the end of this session, you'll have the tools you need to create an animation of animal movement. This course is part of an acoustic telemetry workshop series and includes examples that will help you along the way. Before you get started, make sure to download and install the files required for this lesson using the link in the description below so that you can follow along.
I'm John Pai. I'm the Director of Data Operations at the Ocean Tracking Network, and that means I'm one of the heads of the data squad. We're going to dig a little more into spatial data objects and dealing with spatial data and plotting it. I also find that using Tidyverse and pipes makes for a very readable workflow. It makes for reproducible workflows. It helps me hand off code to people and trust that they're going to be able to understand what I was doing at a glance, which I love that now. For even much more complicated stuff than what we're going to do today, I think that a tidy workflow helps people understand where you're coming from. And we're very grateful to Rob Lennox, who some of you met at Ideas OTN, for producing the first cut of this. You know, the examples that he gives are very close to stuff that you guys will want to be doing with your own telemetry data. So definitely take inspiration from anything that you see here that you like, and then we can try to make it happen for your own data. If not today, then at one of the future OTN study halls. I've cleared out my environment. So there's a little broom up in environment. There's a little broom down in the plots window. My working directory is already in the RL intro folder, but I'm going to set it again anyway, just for laughs. So the first thing I'm going to do now that I've cleared everything out is I'm going to import Tidyverse, and I'm just going to Control Enter that, get that going. And some of the other packages that we're going to use here, one is a library called marmap. It has a couple of really interesting features. One is a bathymetry collection service. You give it a set of bounding boxes, and it will give you the gebco or etopo bathymetry around in that box, so you can have something to plot against, like a backdrop. It also has some interesting calculation capacity where you're going to be able to take 2 points on those bathymetric curves and plot a nonlinear path between them using the bathymetry as your guide. So you can set a limit of boundary where it can't cross. And that's really useful when you're using rivers, when you're trying to plot around rivers, when you're trying to plot around large land masses that you know it's not going to do a little portage over. It's very useful for that. We're going to use lubridate as well, because lubridate is, as we've seen, is a very useful way to handle dates. Later on, we're going to get into animation. So we're going to play with gganimate, and gganimate uses a thing called gifski under the hood. So we're going to make sure that gets in okay. And ArcGeos is a geometry engine that lets us do fast spatial calculation. It just quietly sits under the hood and does that for us. MapProj will let us move between different geographic projections very quickly. And I think we're just using the distance calc from Argos filter. We might not even be doing that today, but it's there just in case. And these are a couple of new packages that I'm going to just briefly touch on if we get to the end. SP dplyr lets you use those dplyr verbs against spatial data objects, which are not natively able to understand them. It's a relatively new package. The last release was May of this year. So I'm excited to try to play around in that a little bit, but it's relatively new to me as well. So we might be learning together on that one. And map view was a request by Kim that I include some map view. So it's new to me as well, but it's a very powerful way to do a quick interactive exploration of your data. So I've set my working directory already. This is a great time to do that. If you're working from your own data, you would just import it from a CSV file like that, perhaps. But I'm actually going to reload the CTrout RGA, and I'm going to try to use the whole 1.5 million rows in my examples. So I'll have a quick glimpse at CTrout. I've run glimpse there, and it tells me, yeah, I've got what I think I have. So I'm going to first talk about handling spatial data objects in R. And so I've run my library commands here again. So we saw when we were looking at the previous module, when we were looking at view and we were looking at lat/lon, that the units were a little funny. That's the universal transverse Mercator or Mercator coordinate system. It splits up the world into these big 6-degree boxes and preserves kind of a local equidistance between points inside of those coordinates. So if you think of the globe as skewing more and more as you get towards the poles, this UTM coordinate system tries to mitigate that by reprojecting these small subsets of the globe into squares. And so it is much better than using lat/lon when it comes to calculating distances between points, which is one of the reasons that people tend to reach for it. It is not so great when data sets overlap a bunch of different UTM zones, these 6-degree zones. So for data sets that are larger, that span larger distances, UTM stops being a good idea. So every UTM set of coordinates within a zone, it's only referenced within its own UTM zone. So once you cross them, it stops making sense pretty quickly. And so what I'm going to do is I'm going to take this data set that I know is an UTM. I'm going to make a copy in my C-Trout data called STS. I'm going to say, I'm going to tell STS that I know that these columns define the spatial coordinates of my data set. So that's where I want you to look for the coordinates. So there's lon and lat. And with this funny little syntax, I'm going to tell coordinates STS, use my lon and lat columns, please, as your spatial reference. And the minute I do that, you'll see that STS has changed. It is no longer a data frame. It is a large spatial points data frame. But even though it knows where to look, what columns to look to define my space, it doesn't know what they mean yet. So first I have to say to STS, your coordinate reference system is UTM zone 33. And here's the ellipse is going to be the WGS 84. My units will be in meters, and I'm going to assign that to my projection string so that when my spatial points data object is working with all these spatial functions later, those functions can look at this and say, oh, your coordinates are in UTM 33. If you don't know which UTM zone you're in, if you get a data set and you don't know what UTM zone it is from, you're actually kind of in trouble because every UTM coordinate system is locally based. So you won't have any clues. They won't be able to plug it into a globe, for instance, unless you know what zone it came from. So here, we're very lucky that we know it came from UTM 33. If you're on the website, there's a nice picture of northern Norway. In 33W is where we're going to be working. So now that I have a spatial points data object here with a proj4 string that tells it, hey, I'm in UTM zone 33. And you can have a look in your environment. You can always look at a variable by clicking the hourglass there, or you can click the arrow to expand what its variables are. So it knows now it has a coordinate reference system metadata value that you can take into these other functions. So what I'm going to do is I'm going to pass my spatial data points data frame into a function called sp_transform. And sp_transform. I'm going to use the question mark on it. You can see how it works. So it wants a CRS object, and it's going to return transformed coordinates using the projection argument. So here I'm going to say, give me this spatial data frame, but make its coordinate reference system EPSG 28992, which doesn't mean much to me. But if you wanted to look and see where it was, epsg.io will tell you that this is a topographic map for the Netherlands and in easting and northing still. So if you do this, if I run this, it takes a second because it's converting every entry in the lat/lon columns into the new coordinate reference system. So if I look at the data frame now, so I switched this back to a data frame so I could open it up and have a look. My lat longs are indifferent and yet still not like you would picture a lat long to be. They are still in easting and northing, but the coordinate reference system has changed to the new box that I've asked it to go into. Now it's EPSG 28992, but that's not a useful box for us. The box that we want, the box that we're going to take out to maps and do things with, the box that matches what my receiver metadata might be, let's say, is lat and long. So we're going to project it into long lat, and we're going to do that CRS now. So we're going to transform our data frame again. And now when we look at it, we can see that the longitude is 5.83 degrees, 4 degrees to 6 degrees. The latitude is 60. This is exactly what you'd expect if you were plotting this globally. So now that we're in the correct spatial reference system for the rest of our data that we're going to combine with it, we can use the boundaries of our lat and longitude to go to a global data set and ask it for other data about the area. So here, I'm going to say, give me a little padding, X. So this is like an amount of, I'm going to go grab a bunch of bathymetry data now from NOAA, and I'm going to say, give me all the bathymetry information between these lat-long bounds. So first, I'm going to make sure that my ST value, which is the converted spatial data object, I'm going to say make sure that's a tibble because I can operate on it the way I expect to be able to with my $ operators. And I'm going to tell it to save in this new bathymetry object here the results of get NOAA bathymetry. And get NOAA bathymetry wants the starting longitude and the ending longitude, starting latitude, the ending latitude, and what resolution. And so the higher resolution you grab, the longer it will take. So I'm going to do resolution 1. But my min, so I'm going to take my starting longitude is the minimum value of lon minus x. My ending longitude is the maximum value of lon plus x. So I got a little bit of boundaries on top of the full range of my data set, whatever that data set happens to be. And then when I run this, it will tell you that it's going to the node, it's going to get the node database. It might take a little while, and then it builds a bathymetric. If you are on Windows, this is something we found out just yesterday. If you are on Windows, it doesn't like having non-integer values in these queries. So there's an alternative thing to run down here, and that's commented out. So if you need to, you can uncomment that and run it on Windows. If the previous command gave you an error, it uses floor and ceiling basically to give whole number values to the arguments here, so that it's not it's sidestepping a very strange bug that I hope they fix soon. All right, so we've got a BGO here. Our BGO is a bathymetry matrix. So what is the class of BGO? The class is bathy. I don't know what bathy is. Let's do what we always do and view it. Uh-oh, I can't view it. It doesn't know how to make bathy into a data frame, and so it can't give me a nice preview of what bathy is. Okay, another thing you can do with just about any variable in R is print it. So I'll just type BGO and print it. Yikes. Okay, looks like I've got some column headers here, and I've got some rows here. This is just a matrix. It's a grid. So what are the dimensions of our matrix? I'm going to call the dimension function. I'm just going to investigate this some more. Okay, it's a grid. It's 125 by 76 values. And then it has negative values. That must mean depth. That's how far below sea level. All right, let's just see if I pass it straight to plot and don't tell it anything else, what happens. All right, it plots when I do that. I'm starting to see some contours. This looks pretty good. This looks like something I might expect to be ocean bathymetry. Let's go. Let's make it blue because it's the ocean. This is looking a little skewed though. Let's see. So there's a function called Autoplot in ggplot2. It is going to look at this type bathy, and it knows a little bit more about how it ought to be plotted. So Autoplot makes a couple of good assumptions about shading and scale of y versus x. And then you end up with a much more interesting looking plot. So now that we're pretty sure we understand what this bathymetry data is, we're going to turn it into that data frame that Vue tried to turn it into and failed to before. And to do that, we're going to use a function called fortify. And it's from ggplot2. It's going to be deprecated soon, but for now, it's all we've got to do the work with bathymetry data. So I'm going to take my bathymetry object, and then I'm going to fortify it. And then I'm going to say, make sure that you're a tibble, which is a unit of data in the Tidyverse realm. So now I have 3 columns. I have X and Y and Z. Instead of my 120 by 70 some matrix, I've got a much longer list that defines each coordinate inside there, and that makes it easier to operate on in a tidy way. But we will still have the default BGO in our back pocket. We're not going to save that anywhere yet. We're just going to make sure we remember to fortify. So with this fortified bathymetry data, we can take it straight to ggplot like we were doing before. We can tell it that our aesthetic is X and Y, that our fill color is Z, so there's X, Y, Z. And then we'll tell it that it's a raster. So can you plot this like a raster for me? And so I'm just going to run these first 4 lines, and it's going to give me a pretty good shaded raster of what's going on this coastline. That's pretty good. But in MarMap, in fact, there's a function called scale fill etopo, which is a bathymetry, a popular bathymetry data set. And that will it will basically do nothing but add a color scheme that's appropriate to bathymetry data. And so when I run it with that just 1 line added, it's going to color the ocean and the land masses properly so we can get a better idea of where we are and what we're doing. And then I can do some of the aesthetic things like adding labels, including a theme, setting my legend position, how big it is and how wide it is. Now that we've explored what we're doing so far, we can start to add the little aesthetics that start to clean up this plot and make it look presentable. And if we like what we did here, we can even, as Caitlin showed us, we can save this output to a variable instead of just showing it. So if I say, I like all of these styling choices, I'm going to highlight this and I'm going to save it all to bplot. And we're just going to put bplot in our back pocket. And then whenever we want to, we can just run bplot and get our plot back. Now, one thing that we did here with bplot, so let's say that we wanted to always have a map of where our receiver locations were. And that's our background against which we're going to do everything else. So I take my same plot as before, and I add 1 more argument. I have geom_point, and the data is my ST object that I built with the nice, the global lat law and reference system. I'm going to say, make it a tibble so I can work on it. And then give me just the distinct latitude and longitude. So now every lat-long pair is just 1 point and not 1.5 million points, which is why this plotted so quickly. Because if I look at data as a tibble distinct, there are only 72 distinct station locations. So now this is much snappier to plot because we've pared down our data set. We're not over plotting our stations. We're just plotting exactly the spots we intend. All right, so we've got bplot in our back pocket. It's a pretty nice representation of our study area. It's got all of our station locations on it. Let's look at a couple of workflows that use Tidyverse verbs to maybe do some things you might be intending to do with your own data. So is my ST a tibble? It is already a tibble. I'm just going to run that again. Never hurts to make a tibble into a tibble. So now we're sure that all of our verbs will work on our ST object. And now I'm going to summarize the ST data in a different way. I'm going to say, in my data, first I'm going to set the date times up properly. So I'm going to use lubridates, yamtams to make my date times into a datetime object. And then I'm going to select everything but the old datetime column and the first two columns. So if you remember, ST here has column X, column datetime as the first two columns. So I'm going to say, don't give me 1 or 2. And then just in case datetime's not where I think it is, definitely don't give me datetime. So this select with the minuses lets you drop any columns you don't want to carry along with you at any point. This is a way you could filter, but we've done filtering already, so I'll grab the whole data set, I won't filter it out. And then I want to arrange the data by date time. So order it by date time so I can operate on it. Group it by tag ID. So now I have, for each fish, the first to the last detection of that animal. And then, so I'm going to add a couple columns with mutate. So we've got our data set minus the old date time, minus the old X index. And I'm going to ask it for 2 new columns. It's going to be lag longitude and lag latitude. And that's going to be, when you use this lag lon and the lag lat, it gives you the previous row in the data frame, that variable in the previous row. So that's basically the previous detection of this animal is going to be in lag lon and lag lat, which is great because the next thing I'm going to do is say, whenever the longitude is not the lag longitude, let me keep that row. So every time you get consecutive detections of an animal at a station, just drop the rows where they're still in the same place. And this is going to let us pare down our data set really heavily. So then if you get 10 detections of an animal at a station, you're only going to get 1 row from now on. And then we're going to make sure that we only have real longitudes so that we don't have the first detection of each animal would have no previous detection, so that would have an NA. So we're going to just drop those to make it easy on our processing. And then we're going to calculate some summary values from that. So for each animal, we're going to calculate their average bearing. So we're going to use Argos filters bearing function to say from this spot to the previous spot, what was the bearing? And we're going to use its distance to say from this spot to the previous spot, what was the distance? And so it's a pretty complicated set of operations here, but if you take it line by line and you read it, it's possible to figure out what's going to happen. And if I run all of this, I will get my ST summary data set. So now we've saved to ST summary 192,000 points. That's somewhat representative in certain situations of the 1.5 million raw data. So if I view, and I'm just do the dimensions, 192,000 of 12 columns. So if I view it, I no longer have an X, I no longer have a date time, but what I do have is a DT, that's a date object. I have a previous lat lon pair. I have the bearing between those 2 points, and I have a distance between those 2 points for each of my subsetted, I won't even call them a summary, but it's a subsetted detection set. So a reminder, when Rob showed us this, he said, look, these points, these bearings, these distances, they ignore land. They're going straight over land. So this is not the be all and end all of summarizing data. It's just a very quick way to explore what your data might be saying before you take it into something a little more savvy, which we should get to do this afternoon. And so now that I've got my data summary, it'll be a lot quicker to work with. I'm going to group it by tag ID. I'm going to mutate it again to make a new variable called cumulative distance, and that'll be the sum of all the distance entries for that animal. So now we'll get an idea of how far that path for that animal goes. And then I'm going to take that and pipe it straight to ggplot and say, ggplot, my X is date time, my Y is cumulative distance, color them by tag ID, please, and plot it with the geom step function. And then I'm also going to use facet wrap from before to make one per species that I have. So group them by species on the plot. So let's see what that will do for us. Here it comes. It always takes longer than you think. So the plot has come through. You can see the salmon not moving very much. You can see the trout moving at varying degrees. Over time, you're watching the difference in movement over time. This cumulative function is pretty good at showing you some patterns if you're looking for patterns. So that's great news. Now there's a question of if an animal is within range of a couple of receivers, it might end up, I don't know if anybody's ever tried to beat their Fitbit by shaking it around a whole bunch, but a similar thing happens here when you try to calculate distance on an animal that's between two receivers. It looks like it's doing a lot of work, but it might not be doing anything. So we're going to do the summary again, but we're going to filter out any distance less than 2. So only give me the distances that are greater than 2. And then we're going to plot it again, but we're going to do a different kind of plot. So we're going to take a different summary statistic. This time we're going to use the bearing, and then we're going to color it by species. And we're going to make it a density plot here. We're going to facet it by species as well, so we'll get 1 color per plot. And we're going to use polar coordinates because our bearing is a degree value, so we want to see it in a polar plot. So if we have explored that one, we can see a trend in the direction in which the animals are traveling. We can explore those trends on our polar plots by species. So these summary values, while they're pretty rudimentary, they're doing good work and they're sensible in terms of showing us a couple of the species related traits that might be popping out in the data, some trends in the data that we might be able to find. You would probably look at filtering steps, like taking a little bit more filtering steps before you start doing these sorts of things, because if somebody was a homebody, it might start to skew the results. If you had an animal sitting next to an individual receiver, if you had an animal that died in range of a receiver, you get a lot of extraneous data that you might have to pull out first. But once you get a data frame and you'd like to start exploring it, these are some of the things you could do to explore that data frame. So that's a good sort of idea of how to use Tidyverse verbs to summarize data and then pass it straight to ggplot and plot it out. And in our back pocket, we still have our geospatial data object that is our bathymetry layer that we're going to come back to here in a moment. But first, another reasonable thing to do with our stations and animals moving between them is to think of them as a network of connections between different nodes. And so we can take the data as we have it now in our summary, because we have the station we're at and the station we just came from. We can take that data and we can sort of start to imagine it as a network of nodes. So if I were to take my summary data frame now and I tell it to group by not just species this time, but also the station and the previous station with our lat-long pairs, and count up how many times we see a species move between those two pairs of stations, I can pass this to a plot in ggplot that has both an x and an x end and a y and a y end. And so this will plot a segment between my previous lawn and my next lawn, my previous lat and my next lat. We'll plot the path between them, those two nodes. So the geometry I want to use will be segment. And I'll tell it to curve a little, no straight lines between the two segments. I'll tell it to curve a bit. Rob used purple here, which I thought was pretty cute, so I'm keeping it. And I'm going to do a facet so I have each species separately. We're going to plot each species separately again. And I'm going to have geom point because you want to be able to see where the nodes are as well. So by using these segment plots with a x end and a y end, as well as the x and y, you can see per species how they move between the space. So the segment is the black lines there, and then the curves, if you have too many segments that overlap each other, you can use the curves to sort of get them all away from each other and sort of start to see the patterns. This is still an unholy tangle that you probably can't make much sense of. So what we're going to do is move our points to the bottom of the plot. So we're going to plot the points first instead of last, because you can see the points are on top here. So let's see if that improves our situation at all. And we're also going to, I neglected to mention it, it was hard to tell which of those segments were more important. So for the plot that we're doing, we added something to the aesthetic. We said, make the size equivalent to the log of n. Instead of keeping them all the same size, we're going to say, plot the thickness as log the number of the connection count. And that shows us with some nice big thick lines, which are the more popular highways here between nodes. And everything else pretty well stayed the same there, so there's not much else to go on. But geographically, this doesn't mean anything. Just by looking at it, it is in lat long, but you can't really get context for where you are. So this is where we can pull out our bathymetry plot from before, and then we add onto the bathymetry plot just the geom segment. And so we'll use the summary, we'll use the group by just as we did before. We're going to keep the log plot. So size n is log here. So that's in our aesthetic for the ggplot. And now we're also going to use a variable called alpha, and this is transparency. So we're also going to use log n for our alpha. So now the less important that connection is, the clearer it will be. And because we started this with bathymetry data that had X, Y, Z, and not X end and Y end, we're going to have to, in our aesthetic for the ST summary data, we're going to say inherit AES is false. So this says I'm aware that my data set here that I'm doing doesn't match the parent plot's data set. And so what I'm going to do is tell you to ignore the fact that my aesthetics don't line up and take my word for this internal aesthetic. And so if you have two data sets that you're plotting two different sets of dimensions against, you have to do this. And we're the same thing, we're refacet it by species. And if we do that, we can see the connectivity of the salmon only network on the map, on the geography itself. And we can see the connectivity of the trout network on the geography itself. This is the very beginning of starting to use this data in terms of network analysis. There's much more you can do. iGraph and ggraph are two good packages to explore, and other people are much better experts in them than I am. But this data is basically prepared if you want to consider stations as nodes and movement between them as edges. You're prepared to walk into some of those more complicated packages by treating your data this way. All right. So some of the bonus stuff. This is, again, I just had a lot of fun with this when Kim handed it to me, so I decided to quickly cobble it in. There's a library called MapView. Lets you interactively explore spatial data really quickly. And SP dplyr lets you use these spatial data frames, use verbs against them. So you can still do your subsetting and your filtering and your mutating against your spatial data object without having to migrate it back into a tibble. Now, we're still not going to plot the entire data set. That would take ages and ages. And it's a lot of overplotting. As we saw, spatially, there's only 71 or so distinct data points. How many? 72 distinct data points. So we're not going to run MapView just naively against the entire spatial points data frame. But if you have an object like STS that is spatially aware, you can pass it to MapView and it knows what to do with it, which is just a beautiful shortcut. So what I'm going to do instead is I'm going to do a couple of SP dplyr subsets and then pass the result to MapView in line, just like we were doing with ggplot. So here we are with our spatial points data frame. We're going to, and then filter just on this one tag ID. So if I want to see where this one animal was, I can run map view against it. And I will wait a little while. And then if the data set's too big, which this one was, it sometimes pops it open in a new browser window. So here I am in a browser window. I'm giving you all motion sickness right now, and I'm sorry. And you can highlight and click on any of the points from your data set that you passed it and explore the features interactively. There are some alternate imageries that you can use for maps: OpenTopo, Esri World, OpenStreetMap. I bet if I had enough time, I could figure out how to carve Esri's ocean base map in here. I haven't done that yet, but I might publish a snippet later on showing how to do that. But it shows you for each of these data points, what are the relevant row values from the data that created them. So there's a trout. It had a length of 41.5. It was seen on this date by this receiver. Now, this is still over plotting because we probably had a bunch of detections of each of these trout at that point. So what are some other ways we can subset? Well, you could say, here's my spatial data object. I'm going to fix my date time again to make sure that I have a LubriDate savvy date time. I'm going to overwrite date time using mutate, and then I'm going to filter on it on my date time that I just fixed up. I'm going to say between May 1st and June 1st, just give me those detections. And before I just pass it to map view like crazy, because I don't know how many detections that'll give me back, I'm just going to highlight the internal and run that to see what I get back. So it looks like I've got about 105,000 rows here. So that's actually kind of a lot for map view, but why not? We're going to do it. This is about the top end of what you want to pass into a web-based map like this. The DOM, the document object model, starts getting really upset with you over a few 100,000 data points. And so it's still cooking for me right here. So it's pretty, there we go. It's pretty intense to throw this many data points at them. So here comes my map, I hope. But while we're waiting for this to finish rendering, we know this is also an overplot because we've got multiple detections plotting on top of one another. And so we don't have to have it be this slow. We can think of other ways to properly subsample our data or properly summarize our data without passing too many points to map view. And so a way we could do that, what is the most succinct way to summarize this data? It's finding individual locations, so just plotting one point at each location. So here, if I just say map view, give me not even just distinct lat lons, just give me the distinct receiver value. How many distinct receiver values do I have? 45. All right. So that's such a small data set, it doesn't even bother with the browser anymore. It just lets me see it in my plot window. And you get the same interactivity, but you don't have to leave our studio. So here's a few separate receiver deployments at that location. You could gin up some summary statistics here in the interim, and those would show up on your tooltip. I bet there's a lot more fun I'm going to have with this package soon. I'll try to, if I do get it up to something, I'll try to release a notebook or a gist explaining some of the stuff I find. I'm excited about it. All right. And the very last thing that I wanted to make sure that we went over is the idea of animating plots. So the other way that we get around the idea that there's so much data hiding underneath these 50-some data points, these 70-some data points, is because telemetry data is just a million things that happen in the same place at different times. So if we can't figure out how to represent a time variable, we don't see a lot of what's going on. So that's where animation helps us out, where we can start to pick frames and sort of draw and animate a picture of what's been happening. So time becomes the time variable again, which is what we like to see. So we're going to go again and pick one animal to follow, and we're going to save that to ST1. So our ST summary, we filtered that down. We've got one animal. It's in ST1. It's 1,500 observations. And for that animal, we're going to start with our background object, our lovely bathymetry from before. We're going to plot it with XYZ, and with the raster, and with the topo, and with the lat, lon, and depth labels, just like we did up at the top. And then, so, we can also check and say, is that what I think it is? Yes, it is. It's the same lovely plot from before. So this is going to be what one of our frames looks like on the backdrop. And we're going to say, so now we're going to plot our points on top. So I'll do that part too. So plot our points on top. There's our station points. And now we don't have to filter ST1 again in here. That's not necessary. But we are going to tell it for our animal's movement data, ST1, we want to use lon and lat as our aesthetic and size 5 and color the points where the animal is in purple. And so all this stuff is just a static plot still. Let me just shrink this down here. So this is all the places our animal has moved across our station all at once. Now we're going to tell ggplot, actually, we're going to animate this. I want you to use this date time as your transition times for this plot. So now it says, look at the date time column, and that's how you're going to decide what order to show these data in. And then I'm going to add a label here. And then this label will be, depending on what the time is in each frame, the label will be the date, and then variably it will be whatever the time is for that data frame. And if I save all that to animation 1, it doesn't plot anything. It's saved it all to a variable. What is the structure of that variable? The structure of that variable is an animation. Come on, here we go. It's pretty big. A lot of metadata goes into our animation. Just a ton. Look at that. There we go. So it is a list of 14 frames. So in those frames are all of our observations. And then ggplot will know to move through these frames and create each of them and stitch them together. But we haven't asked it to do that yet. It's just a variable saying, I'd like to do this in this way. In order to create our animation, we take our set of frames and we pass it to gganimate. And it will run through each frame, render it, and then it will stitch at the end. It'll stitch them all together into a lovely GIF. Here's our lovely GIF. It's rolling through all my frames for me. It's made 100 frames for me. And now, you can see my date is iterating through the frames. You can see the movement through time of the animal across all these receiver stations. And you can facet these out by animal. You can start to use this in an exploratory way to get an idea of what your animals are doing across the space. The GLaDOS package will help you do things like dodge land masses and just generally get a better picture of what might be happening at the transition times between these station detections. But now I think it's a good time to both take questions and then take lunch.
Thanks for watching the Ocean Tracking Network on YouTube. If you enjoyed this presentation, there's a good chance you'll like some of the other videos in this series. Click on the link in the description below for the workshop playlist, where you can learn more about the R programming language and some R packages suitable for exploring and plotting acoustic telemetry data. Keep up to date with our latest videos by tapping the subscribe button or clicking over on this list to see more workshops